Welcome back. As we continue our study of quadric surfaces, we're going to look now at an elliptical paraboloid. So we already did an example in our second video, which we didn't really know what we were looking at yet, of an elliptical paraboloid. But we're going to talk about our standard form. The main thing you want to notice with an elliptical paraboloid is we have an x squared and a y squared, but we have a third variable which is not squared. In this case, it is z. So you could have z squared, y squared, that would be an x unsquared, or x and z, and we would have a y that is not squared, right? So the main difference with an elliptical paraboloid is we have two positive squared terms, and then one term, it doesn't matter, the sign is not squared. So this one only has one intercept. If we look at trying to find the intercepts by, say, letting x and y be 0, we would get 0. That would have to equal 0 for this to be balanced. So we've got 0, 0, 0. And that's the only intercept we have here. For our traces, when we find the traces, we look at letting each of the variables be equal to a number. So if I let x equal some number, x is equal to a number. This is a constant. So having that x squared go away, we end up with a parabola or parabolic shaped situation. So this gives us a parabola. And due to the similar nature, if I let y equal a number, I also get a parabola. But what shape do I get if I let z equal a number? That gives me an ellipse. And that's an ellipse in the x, y plane. In this case, I'm not going to write that there because it would change based on where your variables are. So we've got two parabolas and an ellipse. And what this looks like is what we already have drawn. We have this elliptical shape. And then we've got this parabola rotated around, in this case, the z-axis. So this is what a elliptic paraboloid looks like. All right, let me pull in the picture from the text. So an elliptical paraboloid looks roughly like this. Again, this shape is an ellipse or a circle, and then our traces in the other two planes create parabolas. And it doesn't have to be oriented up, it could be oriented down, facing to the left, or facing to the right. The main thing you want to notice is we have two variables that are squared, both are positive, and then one variable which is not squared. So the next quadric surface is an elliptical cone. X squared over a squared plus y squared over b squared equals z squared over c squared. So this is very similar to if I wrote x squared over a squared plus y squared over b squared minus z squared over c squared equal to 0. Right, so you'll notice we have all three terms squared. We have one negative, or one of the squared terms on the opposite side. All right, so if we looked at trying to find the intercepts here, we're going to find there's only one at the origin, which is 0, 0, 0. And let's consider what the traces might be. So my traces. What happens if I let x equal some constant value? If x equals a value, then we have a constant here. So that would be like saying y squared minus z squared is equal to a constant. And when we have that minus, that's going to give us a hyperbola. And the same thing happens if I let y equal a number. I also get a hyperbola. If I let z equal a number, however, I end up with an ellipse. All right, so what does this look like? Our standard elliptical cone. It's going to look like a cone. We've got this ellipse traveling up, and then down. So it's this conical region traveling up and traveling down, and the trace over on either side, in a sense, is hyperbolic. So you see that hyperbolic trace. Again, I'm going to pull in a picture. So here is an elliptical cone. So we have these lines, or the kind of the asymptotes of a parabola, a hyperbola, which are causing this crossing shape. And then we have these elliptical traces moving up and down. Of course, we could tilt this, have it turned, being around the y-axis or the x-axis. Right now it's centered around the z-axis. So this represents our third quadric surface. I'm going to pull one more in. We'll talk about one more, the hyperboloid of one sheet. So this is a hyperboloid of one sheet. X squared over some constant a squared plus y squared over v squared minus z squared over c squared. And you might say, well, how is that different than what we just talked about, the elliptical cone? Well, you'll notice this is equal to 1. And if I skip back real quick, the elliptical cone, when I moved this over, notice it was equal to 0, right? So the hyperboloid, very similar, equal to 1. So all three are squared, x, y, and z are all squared. 2 are positive, 1 is negative. The hyperboloid of one sheet is equal to a cone. We're not going to bother with the x-intercepts on this because they're pretty tricky. They're not really worth dealing with. But we'll talk about our different traces. Let me give myself more space. So my traces. What happens if I let x equal some number? So if x equals a number, this term becomes constant, and I'm left with the equation of a hyperbola. Same if I let y equal a number. If I let y equal a number, I also get a hyperbola, right? Turning this into a constant, x squared minus z squared, I have a hyperbola in the xz plane. What happens if I let z be equal to a number? That turns this into a constant, goes away, and I'm left with an ellipse. So if z equals a number, then I have an ellipse. So we have these ellipses in this situation. That ellipse is going to be in my xy plane, and we have these hyperbolas going up in both the xz and yz planes. So thinking about my graph, trying to do it by hand, help you visualize it. So we have ellipses, right? We've got these different elliptical shapes here. So we've got one ellipse, and as we go up and down, that elliptical shape, this of course being symmetric, gets larger. We end up with this kind of curved. So it's not quite a cone, it's a little bit bigger in there. That's just messy if I draw those. So I'm just going to pull in the picture. So here is the hyperboloid of one sheet. So you notice in that xy plane, we said we had ellipses, and then we have these hyperbolas coming down on all of the sides. So I'm going to conclude this video, and I'm going to do our last two quadric surfaces, hyperboloid of two sheets and a hyperbolic paraboloid, in the following video.